Welcome. Another question, paper 1. One of the questions that many learners are enjoying answering it, and this is Doppler effect. Remember, in Doppler effect, before you can come to the question here in the question paper, one important requirement for Doppler, the requirement for Doppler is the relative motion. Relative motion. Therefore, if there is no relative motion between the source of sound and the listener, then there is no Doppler. If you are in an ambulance is emitting sound, you will hear the same frequency as emitted, because you and the ambulance are not moving relative to one another, to each other. So there's no relative motion between you and the ambulance. So that's the case. Now, one of the recent question papers here about Doppler is this one. They say a siren of a stationary train, the source is stationary in this case, emits sound waves of a constant frequency of 780, underline it and label it as frequency of the source. A person in a car with a detector accelerates constantly from rest at point X towards the train. No problem. The speed of sound in air, take the speed of sound in air as 340 meters per second. Now this is the setup. The first question, which is number 6.1, we say, name the phenomena that was observed by the listener. They were in the section of Doppler anyway. That was a bonus mark. Doppler effect. Remember, in some cases, you can be asked to define what is Doppler. So Doppler will be about the change in frequency of sound as detected by the listener. Change in frequency of sound as detected by the listener, due to the listener and the sound source moving relative to each other or relative to one another. So that is the case. As the sound source and the listener move relative to one another, there will be a change in frequency that led to Doppler effect. So 6.2, now calculate the wavelength of the emitted sound waves. Remember, in this case, I always tell learners that there's only one formula with a wavelength in it. Is that wave equation. Frequency equals to speed of sound equals to frequency multiplied by lambda. Now on this one, they gave us the speed of sound in air, which is 340. Now they give us this frequency of the sound source, that is 780. They say calculate the wavelength. Then you can calculate the lambda there as 0.44 meters. You get 2 marks. So normally should be 3 marks. The examiner here was very economical with the marks. No problem. You just do it the way you have to do it. Next question for 2 marks again. They say to us, look at this one. They say explain why the observed frequency is higher than the emitted frequency. Now, this case, the examiner was stretching now to check whether you really understand what causes change in frequency. Now we know that what causes a frequency firstly will be the wavelength. Now what happens? You just have to tell the learners that the wavelength of sound waves, that's the first point, wavelength of sound waves decreases or are compressed. That's the first point. Now the second point, the examiner wanted to know whether do we really know frequency. Now if you don't know frequency, you want to answer this, so you won't get the second mark. To say, therefore, as a result, when the frequency, what makes the frequency to increase is because, remember, frequency is the number of, in this case, completed waves per second. Therefore, meaning that now more waves, in this case, per second, or more waves reaches the listener per second. More waves reaches the listener in a way that you'll understand it per second. Remember, frequency, as I say, is the number of complete waves per second. So this will make the frequency detected to increase. Now 6.4.1, they're telling us to say here, the statement is preceding this, at point Y, 83.11 meters from point X, the person in the car measures the observed frequency to be 850. You can see now that the emitter is 780, this one is 850. It's also agreeing that the motion is towards the speed of the car at point Y. Therefore, we're going to use our knowledge to say, use the Doppler equation, FL equals to V plus or minus VL divided by V plus or minus VS multiplied by FS. Remember, if it's away, always say learners must know, away, then you must start with negative over positive. If it's towards, then it will be positive over negative. That one helps to say here now the frequency of the listener is 850, we are told, and then the speed of sound is 340. Because it's towards, we'll start with the positive. The listener is moving, we are calculating that speed, then it will be VL divided by 340 minus, this one is stationary 0, multiplied by 780. Then from here, if you use your calculation very well, find that VL equals to 30.51 meters per second. You get 5 marks there. Very simple, clear calculation. That's the case. Next calculation, that is 6.4.2. 6.4.2. They're saying to us, the last question, calculate the acceleration of the car. Calculate acceleration now, you can tell that the car starts from, in this case, moves at a constant acceleration from rest. Initial velocity is 0. If the initial is 0, the final we just calculated now, it's 30.51. That's the case, 30.51. What else do we know? We know delta x is given, is 83.11. Therefore, they want us to calculate the acceleration. Very simple, you go for equation of motion. Without time, you can see there will be Vf squared equals to Vi squared plus 2a delta x. It's fine. Vf squared will be 30.51 squared equals to 0 squared plus 2a multiplied by 83.11. According to this one, if you use your calculator very well, then a will be 5.60 meters per second squared. That's the acceleration in this case. Very important, Doppler. Remember, in this case now, this is the last question. In this case, we are not given the question of the distance star. So in a nutshell, distance star, remember, distance star will be now examined only in the question of the redshift. Please, that is examinable one. During redshift, this is what you need to know, is that the movement of the distance star is away. Distance star must move away. Now, if it's moving away, what happens to the frequency? The frequency, according to Doppler, movement, if it's away, the frequency decreases. Decreases. Fine. When the frequency decreases, what happens to the wavelength of those waves? Then the wavelength will be now stretched. Increases. Now, when the wavelength increases, the next part will be what happens to the universe now. We'll have the universe is expanding. expanding. But very important, these two. So you must know that. So redshift is when the frequency decreases and the wavelength of those sound waves increases. So the movement is away. Very important about the redshift. I hope you get it. And the one that is examinable is this one. The blue shift, we know, yes, the movement is towards the earth, is the opposite of this. But what is examinable in the final analysis is this distance star. The uses of Doppler, remember, of Doppler, which is not featured here. Then we are using Doppler in sonar 2. You must mention it explicitly. Sonar to measure the heartbeat of the fetus. Then the next one will be the Doppler flow meter. Very important. 2, this one measures to measure the rate of blood flow. So Doppler flow meter measures the rate of blood flow, whereas the sonar measures the heartbeat of the fetus. Please know these two uses of Doppler in medicine. So Doppler in medicine. So they can ask you this type of a question. Please, when asked, get it right. It's not that difficult. It's very easy. Doppler, one of the sections that you can get all the marks correct. Good luck until we meet in the next sessions. Bye.